Hello everyone, in this video I will be explaining assignment 3 from WTW 218-2020. In our very first question, they ask us to consider a function from R3 to R, where fx, y, and z is defined by this, and they say let k be equal to alpha plus 1. Now alpha depends on your student number. For this question, I will just assume alpha is equal to 5. It will work similarly for every other question. Now, unfortunately, in this assignment and in this question, we did not give you a marker location for this question. That really helps when you want to know how much time and how much effort and how much detail you need to give to a question. Now, this question only counted 2 marks, which means you don't need to give all the details when sketching the level set L6 in my case. So what we can do is we can write down the definition for L6 and then see what we have. So L6 is the set of x, y, and z in R3 such that x squared plus y squared plus 2z squared is equal to 6. Now, this kind of looks like an ellipsoid, and you can manipulate this equation here to make it look like an ellipsoid. And to do that, you just divide the entire equation by 6 to get the right hand side equal to 1. So then it will be in the form. So after dividing by 6, we get the equation in this form, which is an ellipsoid with x-intercepts minus 6 and positive and negative square root 6, y positive and negative square root 6, and z positive or negative square root 3. So after some practice, I sketched the ellipsoid, and as you can see, the intercepts and the shape is what is most important. So you got a mark for the shape and a mark for the intercepts, and that's why I indicated them everywhere on the question. For question 2, they give us a set D defined by this, where the absolute value of x is less than 3, the absolute value of y is less than or equal to 2. They ask us to sketch the boundary of the set, and then also is the set open or closed. So I'm first going to discuss the boundary, and then I will discuss whether it's open or closed. Now, before we sketch the boundary of a set, you can go ahead and try to do this automatically. You first have to sketch the set, because when you have a set, it is very easy to determine what the boundary of the set is. So I'm first going to sketch the set, and then I will sketch the boundary of the set. So I will have 2 sets of axes. Let's start here. So if I look at this side, it tells me that x must lie between minus 3 and 3. So minus 3 and 3. So, that's a mistake. Because it is strictly less than, it means it is dotted lines, because x cannot be equal to negative or positive 3. So that's why I need my dotted lines, or not solid lines. So we know that x lies here. Now I'll use a different color. Y lies between negative 2 and 2, but included, meaning that the lines will be solid. So this is 2, this is negative 2. I can have solid lines because it's less than or equal to. And y lies here. Now the set D is where these 2 colors intersect. So if I use a highlighter, it's over here, on the inside here. Sorry, there. That is the set D. So we first sketch the set. Now please note that a set and its boundary go hand in hand. A set can contain its boundary, and a set can contain pieces of its boundary, or a set can contain nothing of its boundary. But that still means that the boundary exists. Whatever the set is, the boundary of that set exists, whether it is included or not. So I'm just going to clean up a bit. So now that we have the set, we can sketch the boundary of the set. So we know x goes from -3 to 3. Y goes from -2 to 2. And the boundary is basically everything on the outside. Now what you can do is you can just indicate it on this sketch here by maybe making it just like a thick line, a thick border around here. You can do this and say this is the boundary, or you can resketch it and then just say that is the boundary. You just have to indicate what is the set and what is the boundary. So I'm just going to make another one. So this turquoise color is my boundary. So I can write this is my boundary to answer the question, and this is my set. For the second part of the question, we are asked whether the set D is open or closed. Now, before I answer that question, I just want to give some examples of sets and then say what they are. So I've just sketched some sets just to talk about whether they're open or closed or neither, because a set can be open, closed, neither open or closed, or it could be not open or not closed. Now, these things go hand in hand in a way. I will explain this. So set A contains all of its boundary. There are no dotted lines. This could be something that has a less than or equal to sign or an equal to sign, almost like an ellipse in 2D. So this set A is closed because it contains all of its boundary. Think about a present that is fully wrapped. Same with B. This is also a closed set because it contains all of its boundary. Now by boundary, I mean this. This whole area is the boundary. Now I did not indicate this, but I assumed the inside of the set. So let me just do that. So for instance, let's do that for A. It could be the outside as well, but let's just keep it simple for now, just the inside. C could be this as well, and then D, something like this. So let me get back to it. So as I've said, A contains all of its boundary, meaning it's closed. B contains all of its boundary, meaning it's closed. C contains none of its boundary, meaning that it must be open because it contains absolutely none of its boundary. This is like a present that's not been wrapped at all. And then you get D. D is a set that can be written as not open because it is not fully open. It is open on this side in a way and closed on this side in a way. That's why you can say that it's not open. Similarly, you can say it is not closed because it's partly closed but not fully closed. So this is where it is closed and this is where it is open in a way. You can think about it. That's why it's not open and not closed. You can always say, that it is neither open nor closed. It's kind of like a present that I wrapped and there is a little bit left because I didn't measure the wrapping paper very well. That is a set that is neither open nor closed. Now to answer the question of is D an open or a closed set, we have to look at the boundary. Does it contain its boundary everywhere or does it not contain its boundary everywhere? Now if we look at D, this is what I've sketched before. It contains its boundary along here. I'll make it thicker so it's clearer to see. It contains its boundary around here. And it contains the boundary over there. But it does not contain its boundary over here. Meaning that D cannot be open. It cannot be closed. So it is neither open nor closed, or you can say that it is not open or not closed. So all the possibilities are D is not open, D is not closed, or D is neither open nor is D closed. For question 3, we are asked to prove that the limit of this expression is equal to 0. Yet again, we have an alpha involved, and alpha depends on your student number. I will just pick alpha equal to 5, but the question will work out similarly for any alpha. I can actually leave alpha as alpha because it makes no difference. And then I'm just stating that this expression over here is my fxy. Now, when we're asked to prove that a limit by definition, we always start with the absolute value of fxy minus r. So I'm going to start there. And this is equal to x squared plus alpha plus 2. I'm going to leave the alpha. Let's see what happens. Plus y squared sine of x plus alpha. This is in my way. Let me just erase it. Minus 0. And that's my absolute value. So this, the triangle inequality tells me that the absolute value of all of these terms, the sum of all of these terms, is less than or equal to the absolute value of each individual term. Sorry, that's an absolute value. Let me not split it up yet, just to not skip steps. So x cubed plus y squared sine x plus alpha. Now, a lot of people would just take away that sign now, and that's really incorrect. You need that absolute value of sine on its own before you can say that it is less than or equal to 1. So what I mean by that is I'm just gonna, well, this absolute value of a square is positive, so it's just the absolute value, so it's just x squared. I don't know whether this is positive because alpha could be, it actually will be positive, but let's assume we don't know this. Let's assume alpha is an element of R. So then we get the absolute value of alpha plus 2, and then we have the absolute value of x cubed plus y squared. Yet again, the absolute value just falls away because y squared is positive. And then the absolute value of sine x plus alpha. Now I can say, well, I know that the absolute value of sine for any angle is less than or equal to 1. So this expression will be less than or equal to x squared plus alpha plus 2 absolute value of x cubed y squared, because this is less than or equal to 1. Now, what do I do now? Oh, I forgot a plus. There needs to be a plus there, otherwise we have problems. So now we can restrict things, make things nice so that we have squares. Now, why do we want to have squares? We want to have squares because in our definition of a limit, the norm we use is the Euclidean norm, which we have squares in. So that is why we always want to work towards squares. And the reason why I can limit things is because between -1 and 1, every other polynomial of higher order, so the higher the order, the lower that polynomial will be. So I'm quickly going to make a sketch to illustrate. So after I've sketched some polynomials, we can see that between -1 and 1, x squared has a property that it is greater than any other polynomial of greater power. Please note that these only work for n of natural numbers. So basically n x cubed, x to the power 4, assuming obviously that they have absolute value. You actually don't need the absolute value, but let's not get into that. So this is the property that we have. Now we could go to x, because x is obviously greater than this between -1 and 1 absolute value of x. But we want x squared, as I've said before, because the norm that we use in our definition of limits is the Euclidean norm, and in that norm we have squares. So let's continue. So now you can say, if I restrict x to be less than or equal to 1, then my statement above, x squared plus alpha plus 2 absolute value of x cubed plus y squared, this will be less than or equal to x squared plus absolute value of alpha plus 2 x squared plus y squared. Now we can add the two x terms together. So we can say this is, okay, this is a bit complicated because I have alpha, but I have that absolute value, but let's just write it like this. This is just some positive thing, x squared plus y squared. And now I can just say, well, this is less than or equal to 1 plus alpha plus 2, absolute value, x squared, sorry, bracket, plus y squared, because I'm basically just adding some constant, positive constant of y squares to the equation. And this is then equal to 1 plus absolute value, sorry, plus 2. And this is just x squared plus y squared is just our norm squared. So now that we've written fx minus L, the absolute value of fx minus L up here, as bounded above by some constant multiplied by our norm, we can actually now rewrite our definition and show by the definition of a limit that this limit is equal to 0. So how do you go about that? Well, the first thing you always do is you say, well, let's fix epsilon to be greater than 0. And now we have to pick a delta. So let delta be equal to, now, because we restricted this x over here, our delta needs to make sure that this is satisfied. Now, I'm going to restrict delta to be the minimum of 1 and something else. I'll show how that minimum makes my x valid. So the minimum of 1 and in my case, so after some playing around, you can say, okay, well, I want this to be delta, and then you kind of think, what do I need to pick my delta to be? And if I had to guess, it would be the square root of epsilon over this whoopsie daisy over this constant over here. So now that I've picked my delta in such a way, what does this actually mean? It means that my delta is less than or equal to 1 and my delta is less than or equal to the square root of epsilon over 1 plus absolute value a alpha plus 2. It satisfies both of these things. So how does this statement, if this norm is less than delta, does it ensure that the absolute value of x is less than or equal to 1? Because if the absolute value of x is less than or equal to 1, then I can use all of this. If it doesn't, then I cannot use all of this. So I know that the absolute value of x is less than or is equal to the square root of x squared. And this is less than or equal to the square root of x squared plus y squared, because y squared is greater or equal to 0. And this is exactly that norm and this is less than delta, and delta is less than or equal to 1. So this if statement ensures that the absolute value of x is less than or equal to 1. And that is why I may use this, which I will call A. So we may use A. And now we just rewrite it basically. So we say absolute value of fx minus L. This is less than or equal to, now let me see which one I want to use first. This is up to you. I'm just going to go with A. And I can say this is from A because I've just shown why I can use A. And this is, this could be A as well. You can write that down as well, sorry. So this is just, I'm just going to write it again, is equal to 1 plus alpha plus 2, the norm of x y minus 0, 0 squared. And this is less than delta, strictly less than 1 plus alpha plus 2. Sorry, that's a bracket. And this is delta squared. And this is less than or equal to. Now I'm going to use the second part. So let me call this B. So this is less than or equal to 1 plus alpha plus 2, absolute value. And then I'm just substituting in epsilon over 1 plus absolute value alpha plus 2, square root squared. And this is just equal to epsilon. So then I can say, by the definition, since this holds for every epsilon greater than 0, by the definition of a limit, we know that this holds. Sorry.